Since we're talking about solutions, we need to discuss the heat that is either released or absorbed when a solution is created. So when a solution is formed, an energy change occurs. The reason for this energy change is because the solute and solvent particles experience a change in attractive forces. So again, that's using a lot of our vocabulary that we're learning in this chapter. Here I've got some pictures to go along with that. So if we're talking about putting salt in water and making the solution of salt water, we have to know that water is polar, and water also experiences hydrogen bonding with other water molecules. And those hydrogen bonds are pretty strong, and that keeps water attracted to water. What's also a very strong attraction is the attraction of this sodium atom right here to this chloride atom right here. It's a full positive and a full negative, and they are extraordinarily attracted to each other. Well, when you mix salt in water, what happens is the hydrogen bonds between the water molecules have to break, and that takes energy. Also, the sodium and the chlorine have to kind of disattach from one another. And the reason that happens is because the water molecules become attracted to the ion of opposite charge on the opposite end. So again, we have our sodium atom, and now these water molecules have broken their attraction with each other and have formed a bigger attraction, a stronger attraction with this sodium ion here. And we have all of these negative oxygens, those partial negative oxygens on every water molecule, pointing toward that full positive of that sodium ion. And we have all of these hydrogen ends of the other water molecules, the partial positives, attracted to this chloride ion with its full-on negative. And that's what happens when we make a solution. So we have breaking of solutions, and that takes energy. And then the forming of these attractions over here with this partial negative and this full positive, and these partial positives with this full negative. And that releases energy. So you have this balance of breaking, which takes energy, and forming attractions, which releases energy. And whichever one is bigger, we can describe a solution as either endothermic or exothermic. So if the heat of solution is positive, and we assign values to numbers based on which direction the heat is going. So positive means heat's being absorbed by the system. So heat is being added to the system. It needs that heat to break those attractive forces. And we would describe that as endothermic. It requires more energy than it's actually going to release. These types of reactions would feel cold to the touch. So this would be like one of those ice packs that you find in a first aid kit, where you're either going to pop a vial or shake the two ingredients together, and it all of a sudden feels cold. Well, the reason it feels cold is because it is absorbing heat. It needs a lot of heat to break those attractive forces, and not as much energy is being released when they form their products. If heat is being released, we assign it a negative value. So that gives us the direction in which heat is going. So heat is leaving the system. Heat is released. It's given a negative heat of solution. It'll have a number, and we'll see these when we get into thermochemistry and our study of that. But heat is released. It's going out into the surroundings, and this is going to feel hot to the touch, and we call that exothermic. So if heat is being absorbed, it's endothermic. So the heat, and that's what therm means, goes endos. If heat is leaving the system, heat is therm again, and it is exiting, so the heat leaves the system. And again, we'll see this more when we get into thermochemistry, but do yourself a little bit of favor and remember these values here that I have underlined. It'll make your job as a student a whole lot easier if that's the case. All right, so we've talked about hydrates before, and those are ionic compounds that have water molecules trapped inside. We're going to talk about these again because it gives us a chance to revisit the math and some of the nomenclature. So I'd like for you to think about this for just a second and name this hydrate. Just write it down on your paper. So we have to name the ionic compound, and you should have recognized that we have sodium, and then this is our polyatomic ion acetate. So this is just sodium acetate, and then we give a prefix for the number of water molecules, and the prefix for 3 is tri, and then the way we represent a water, those water molecules trapped inside, is a hydrate. All right, so sodium acetate trihydrate. When we talk about these hydrates, we discussed how we could calculate the percent mass of water in a hydrate. The way we find percent of something in a percent composition is the mass of what you're looking for over the mass of the whole thing. And in the case of hydrates, what you're going to do is the mass of all the waters. In this case, I have 3 of them. The way we find that mass is it's going to be the mass of water, which is 2 hydrogens and 1 oxygen. Each hydrogen from the periodic table is 1.01, and each oxygen is 16. Or you could have just memorized that the molar mass of water is 18.02 grams per mole. And since I have 3 of them, it's going to be 3 times that. And that's how we ended up with this number right here, that 54. Then you're going to divide that by the mass of the whole compound. So that's going to be the mass of the ionic compound plus the mass of those 3 waters. So I also put that 54 in right here as well, and I just found the molar mass of that ionic compound. Of course, with every percentage, it's part over whole times 100 to give us our answer. And this one we would say as, let me see if I can make this, 39.72% water by mass. So it's almost 40% water, that entire compound. All right, so that's the percent mass in water. We could talk about percent sodium acetate anhydrous, which would be without the water if we were making a solution. We could talk about the percent hydrochloric acid in a solution. We could talk about the percent sodium chloride in a solution. Another way that we talk about how much of something is in a particular amount of liquid, especially when we're making these aqueous solutions where we use water as a solvent, is through 2 terms, molarity and molality. So these describe the concentration of solutions. How much stuff is there in a certain amount of water, or whatever our solvent happens to be. By far, the most common is molarity, and that's the one we're going to talk about first. Molarity is represented by a big M, capital M, and just like its name implies, molarity, it involves the moles of the solute, and the moles of the solute per liters of solution. So moles of solute over liters of solution. Molality is represented by a lowercase, I call it a fancy M, but it is italicized. The closest I could get is this on the computer. When I write it, it'll look a little more like this. So that is molality. Now, molality isn't as common when you're working out in the chemical industry, but it does have its purposes. There's a certain mathematical problem that can only be solved using concentration expressed in molality. And again, as its name implies, it does involve moles of solute, but this time it is divided by kilograms of solvent. In these particular problems, it is very important to identify solute and solvent first. And sometimes that they tell you the solute, sodium chloride, but more often than not, you're just going to have to get it from the context of the problem. What is being dissolved, and that will be your solute, and then what is doing the dissolving, and that is your solvent. And you really just want to write it out. This is my solute, and this is my solvent. And the rest of it is just being very conscious of what your units are. The solute has to be in moles, and the solvent has to be in kilograms. Now, because we have 3 things here, we can use the triangle trick to help us with this. So molarity is going to have a triangle that looks like this. Now remember that in order to use the triangle trick, what you do is you cover up what you're looking for. So you want to check it against a known equation. So if I'm looking for molality, I would cover up that M and I would see that it's going to be moles of solute over liters of solution. And then I could rearrange that equation. If what I'm looking for is my solute, then I cover that up. Here, it's going to be molality or molarity times liters of solution, and that will give me my moles of solute. Again, being very conscious of your units will help you out. Now, you can kind of see where some of this is going. You know, having me as a teacher for as long as you have, that when I talk about a solute and give you problems with this, I'm probably not going to give you moles. I'm going to give you grams. And you are going to have to solve for moles. And you're going to have to know to do that. Also, liters of solution, you can probably guess what I'm going to do to you when I give you these problems. I'm going to give you milliliters, and make sure that you remember and are very conscious of these units. And a lot of times in labs, we are dealing with milliliters instead of liters, so you do have to be conscious of that. Also, we can do the same thing for molality, and it works the exact same way. Again, you want to be conscious of those units. The solute is in moles, and the solvent is in kilograms. I will probably give you the solvent in grams from time to time, just to make sure that you're paying attention, give your brain a little workout. If I'm looking for my kilograms of solvent, what I'm going to do is cover that up, and it would be moles of solute divided by my molality, and that just shows you how the triangle works as you go through and work these problems. So I'm going to do a couple, and then we'll talk about some of the modifications that I could make with these. So the first one is a molality problem, and again, with molality problems, the first thing that you want to do is you want to decide what your solute and your solvent is. We can use our triangle for this. In this case, it says, what is the molality? So this is what I'm looking for, so I cover that up. And molality is going to be moles of solute over those kilograms of solvent. And go ahead and write that formula out, and that way you know and are reminded exactly what the units need to be in. So let's identify what we have. I have a solute, and I'll have a solvent. All right. What is the molality of a solution composed of 13.0 grams of sodium chloride dissolved in, there's my clue, 500 grams of water? So what is being dissolved is my sodium chloride, and I have 13 grams of that sodium chloride. And my solute is, that is my solute. And what's doing the dissolving is the water. And I can tell you right now, if water is present in a problem, it is going to be your solvent. So we have 500 grams of water. Okay, now a couple of things I need to remind you of. Solvent, here, this particular one, when we're dealing with water specifically, the density of water is 1 gram per milliliter. So that means every gram of water is 1 milliliter of water. So I could have said 500 milliliters of water, and you would have been able to just exchange milliliters with grams because the density of water is 1. But again, that's only for water. All right, so we have our solute and our solvent. Now we just have to make it match this problem. If we look at our solute, we need that in moles, but I have it in grams. So what we're going to have to do is convert grams to moles. How do we convert grams to moles? Molar mass. So we're going to be using that periodic table. So 13 grams of sodium chloride, and I need the molar mass of that. Sodium is 22.99. Chlorine is 35.45. So the molar mass of sodium chloride is 58.44 grams per mole. Grams are here, so grams have to go over here, and it's 58.44 grams in 1 mole of sodium chloride. Grams cancel out. 13 divided by and I need 3 sig figs because I want to maintain the same number of sig figs. So 0.222 moles of my solute. All right, so that's going to go right here. Now I'm going to divide that by my kilograms of solvent. We have grams, not kilograms, so we're going to have to convert. So in order to go from a base unit to kilo, we have to move the decimal 3 places. Make sure you remember how to do that. If you need to write the King Henry's daughter bakes delicious chocolate muffins on everything on the top of your paper, on everything you turn in order to get this right, do it. I don't care what you have to do, just get it correct. So we're going from base unit to kilo there. So it's 0.5 kilograms of my, solvent, which is water. Now this would be, that's why I put that zero there. I wanted to keep my sig figs. So now all we need to do is divide our moles by our kilograms of solvent. And I ended up with 0.444 molal. And that's how we would say that. Okay, so you put the symbol there, and it is pronounced molal. Okay, so that's how you do a molality problem. This is a straightforward type of calculation that I went through here, but I could ask for any of the pieces within this problem. So if, in this case, I had been looking for, if they had said, how much sodium chloride would I need to dissolve in 500 grams of water, so they would give me this. They want to know how much of the sodium chloride I would need to dissolve to get a molality of this. Well, I know that they're asking about my solute because you want to go about this problem the same sort of way. Identify what your solute and your solvent is. In this case, my solute would be how many grams of that sodium chloride. So in this case, I'm going to be solving for my solute. If we go back to the problem, my solute is going to be expressed in moles. So when I do this calculation to solve for my solute, the answer will come out in moles. But they don't want moles. They're asking about grams in my made-up problem here. So what we're going to have to do is just convert. When you get moles, just convert it to grams using that molar mass. So what we would do is cover up moles of solute. It's going to be molality times your kilograms of solvent. So my moles of solute would be equal to molality times kilogram solvent. And I would end up with my molality of 0.444 times my kilograms of solvent, 0.5 kilograms of that water, and that would give me 0.222, and you have to know from the formula that the units come out in moles. And it's moles of my solute, so it's sodium chloride. And then I could just convert moles to grams using molar mass in the same sort of way that I did up here. And the same thing could be said if I went to work a problem that was in kilograms of solvent. Again, the biggest key to success is identifying your solute and your solvent, and it makes those problems much less confusing. But they're pretty simple problems, even though that I've talked about them for quite a few minutes here. All right, now let's talk about work on a problem that deals with molarity. Molarity is by far the most common type of concentration problems that you will do. And they're in multiple different formulas, especially from here forward in our study of chemistry. So our formula for molarity is equal to moles of solute over liters of solution. So we still want to be able to identify our solute in here. It's just we don't have the trouble with distinguishing it from our solvent, and it makes them slightly easier. So what is the molarity of a solution composed of 20 grams of sodium hydroxide dissolved in enough water to make 2 liters of solution? So I'm looking for my molarity I cover that up. Molarity is going to be equal to moles of solute over liters of solution. Well, my solute in here, it is sodium hydroxide because it is dissolved in water, or enough water to make that 2 liters. So my solute needs to be in moles according to the formula. No problem. I ended up with 20 grams of that sodium hydroxide, and I'm just going to convert it to moles using molar mass. Sodium is 22.99, oxygen is 16, and hydrogen is 1.01. Add those up together and I get a molar mass of 40 grams in 1 mole of sodium hydroxide. So 20 divided by 40, I think I can do that one in my head. That's going to give me 0.500, to keep with my sig figs, moles of sodium hydroxide. That's my moles of solute. Oops, sorry. Moles solute. Then I need to divide that by my liters of solution. It is specific to liters. Now in this problem I kind of made it easy and I put the volume in liters, but quite often that is in milliliters. So I could have put 2,000 milliliters, and Millie, King Henry's daughter, bakes delicious chocolate muffins. Millie's way over here, and to go back to the base unit, 1, 2, 3. So 1, 2, 3, that would give me the 2 liters. All right, so 2 liters of solution. And what we end up with there is 0.250 moles per liter, which is molarity, and we would pronounce that molar. Okay, that's how you do a molarity problem. Again, I'm going to go through a modification to this problem to show you how another one might be done. When I make up a solution, like say for one of our labs, usually what happens is I know the molarity that I want. And I know that how much of the solution I need. What I need to know is how much of my solute do I need to dissolve? How much do I need to weigh out? So again, this is going to be a question of how much solute. Well, in the formula, the only thing that has to do with my solute will come out in moles, but that's okay. If I can get the answer of how much solute in moles, I can easily convert it to grams using molar mass. So if I cover up moles of solute, and again, it really is helpful if you write out the formula, it keeps you on track, is equal to molarity times liters. And you're going to do this calculation a lot as we go forward here in chemistry. So it's easier to get used to it now. So my molarity in this particular problem, they would have given me as 0.250 molar. And they would have also given me the amount of the solution. So I would just plug those in. Times my liters of solution. And moles times liters is, or molarity times liters is going to give you moles. And so you're going to end up with 0.500 moles of your solute, which is sodium hydroxide, because you paid attention in that problem. And since I had that, I could convert it, go from moles to grams using molar mass and just one more step in dimensional analysis. And so it would just end up looking like this. In 1 mole, there are 40 grams of sodium hydroxide, and I would come out with those 20 grams that I would need to measure out. All right, so those are dealing with concentrations and specifically solid solutes dissolved in a liquid solvent. We have one more because sometimes the solutions that we have are liquids in the back. This is specifically true of acid solutions. So we're going to talk about 2 terms, concentrated and dilute. You're going to need to know the difference between those two. Concentrated solution. A concentrated solution is one that has a lot of moles per liter. So a lot of stuff. You can think about concentrated orange juice that you can find in the freezer section of the grocery store. Basically, they've taken all the water out, and so it's just really orange. And then if you want to make orange juice and actually drink this, you dilute it, which means you have less moles per liter. Now, when we're talking acids, what I happen to have in the chemical supply room as far as concentrated acids, I have hydrochloric acid at about 12 molar. So 12 moles per liter. That is a really high number just because you're not used to knowing. But 12 is a very concentrated solution. Dilute, anything really under 1 molar we would consider really dilute solutions. All right, so the way we work with these, and if I have a 12 molar solution, I would never bring that out and give that to you guys to do a lab. So if I needed to dilute that and make a solution from that, I'm going to have to measure out a certain amount of my concentrated solution and mix it with water to dilute it down to something safe that you guys would use. And so the formula that we have and the formula that is given to you on your reference tables is M1V1 equals M2V2. I like to think of them more like this. MCVC equals MDVD. So we have our concentrated molarity times our concentrated volume is equal to our dilute molarity and our dilute volume. So if we look at this problem here, it says how many, first we need to identify which solution we're dealing with. So you want to look at the molarities. So I have a 0.5 molar solution and a 0.1 molar solution. The one that has the higher number is my concentrated one. So this is my concentrated, and this one is dilute because this one has less moles per liter. Now, if I read it, how many milliliters of this concentrated solution? So I am looking for my dilute volume, and that is very often the case when we work these types of problems. Would you need to dilute to make 100 milliliters of the dilute solution? So, oops, I labeled that one wrong. We are looking for the volume of the concentrated solution. I said it right and labeled it wrong. There we go. The volume of my dilute solution is 100 milliliters. That's what I'm going to end up with. So I'm going to go ahead and solve my problem. Go ahead and rearrange my formula so it can just be plug and chug. And I am solving for how much of this concentrated. So I need to move everything away from that, meaning I've got to divide both sides by my concentrated molarity. Now it's just plug and chug. I've got my dilute molarity, which is 0.1 molar, times my dilute volume over my concentrated molarity, 0.5 molar. Molarity cancels out. All I'm left with is milliliters, and that makes sense for volume. So ended up with 20 milliliters. So I would measure out 20 milliliters of my concentrated hydrochloric acid solution. I would have some water in a beaker because we always want to add acid, never add water to acid. We talked about that with the safety rules. So we would take our 20 milliliters of our concentrated solution, add it with some water, and then we would bring up that final volume to 100 milliliters, and then we would have exactly 0.100 molar solution. So that's how you deal with concentrations, and really all you need is some practice. These formulas are given to you, so you don't have to memorize them, but you do have to know how to use them. So I do suggest that you take time and practice these and make sure you keep up with your units.